Port this computer. Log out. Laptop. Preview laptop. Right. Okay, so we're in chapter something 10 of 11. We're almost there. Okay. Now, if you did your homework for chapter 9, you'll see that a lot of what that was is on there, and even more so on the online version. So it's important to do your homework. It gives you an exposure to it. So it's not just an extra 5%. It actually gives you additional time to play with the concepts. And I was just looking at the homework for this, and it also is going to help you a bunch too, to help understand the concept. So the last thing we were talking about was how we could take a compound and get two different isomers by switching the mechanism. And if we did our Markovnikov's mechanism, the hydrogen is going to go on the least substituted side, our bromine is going to go on the more substituted side, and we get the secondary alkyl bromine. But if we change the mechanism, we change it to a radical mechanism, it goes the other way. It goes to where the bromine is on the primary carbon and the hydrogen's on the secondary carbon. Now, this might, if you want to remember it as anti-Markovnikov because it looks backwards, that's good. However, as we looked at the mechanism here, we know that our radical reactions can only do two things, right? Extract a hydrogen and add to a double bond, creating another radical. So we have two things that can happen. But in every radical reaction, three things, there's three stages. Initiation to create your radical. Then we have propagation that hopefully goes to products, but it always generates another radical. And then termination, that's where you lose radicals. And that usually happens at the end of the reaction. And sometimes it makes productive materials and sometimes it doesn't, okay? So when we were looking at here, we saw that once we got that radical abstracting the hydrogen from bromine, bromine became a radical. And that bromine radical wants to add across that double bond, okay? Well, in this case, bromine is the electrophile and the double bond is the nucleophile. And so it's going to add across that double bond to generate the more stable radical. So in that case, we're going to generate that secondary radical. So that's why the bromine ends up on the primary carbon, okay? It's coming in as an electrophile. The electrophile is attacking our double bond and generating the most stable intermediate. It's in the carbocation in the other mechanism, it's a radical in this mechanism. And so the secondary radical is more stable, okay? And so then we can have hydrogen abstraction to give us our final product right here. So in truth, the bromine is acting like the electrophile. And so the bromine adds on the carbon with the most hydrogens. In the other mechanism, hydrogen has the positive charge. So it is the electrophile and it ends up on the carbon. So technically it follows Markovnikov's rule, but it looks backwards. So if you want to remember it as anti-Markovnikov, that's fine. But note that the mechanism states it actually follows Markovnikov's rules, but it does give you the other product. Okay, so we can see that kind of helps us in some things, but also hurts us in others. For example, we take this alkene here, and it was one that we played with when we did alcohols, and we can make a primary, a secondary, and a tertiary alcohol with it. Well, it turns out the only thing we can make with this is a primary and a tertiary, because of that 1,2 hydride shift, because we generated that carbocation. Okay, so now we have two things that radicals can do. We have 3 steps in every radical reaction. And now let's talk about stereochemistry. Okay, so stereochemistry is analogous to that of carbocations because the shape of our radical is analogous to a carbocation, except instead of having an empty unhybridized p orbital, we have 1 electron in there. And that's an unhybridized p, so it's half the time on the top, half the time on the bottom, which means when it does a radical extraction, or when it reacts with another radical in a termination step, it can be 50% of the time on the top or 50% of the time on the bottom. So what that means is we have racemic mixtures. You cannot control it, there is no control. okay? So if you have a non-chiral alkane going through this radical substitution, that radical forms, and then when it gets substituted or attacked by the other thing, it can go on either side. So now it doesn't matter where that hydrogen is when you abstracted it, you rehybridized, and now you can attack from either side, just like a carbocation. Now, if a chiral center gets their hydrogen abstracted, again, it goes through that intermediate, it racemizes the reaction still. You can start with nothing that's chiral and end up with a mixture, a racemic mixture. You can start with one isomer, RRS, and you'll end up with a racemic mixture of the product, okay? And then when you have an alkene undergoing that, you actually get a racemic mixture of enantiomers, or you can. If both of the carbons end up being chiral, you will have a racemic mixture of enantiomers. I mean, no, a racemic mixture of enantiomers for wherever the center was. Sorry, I did not say that correctly. So that when you have something like is this, where you have it coming from the top, you'll make the R, and coming from the bottom, you'll make the S. And so that's why we're going to end up with our mixture there. Okay, if the chiral center is present but does not go through the radical intermediate, it does not change. It might change RRS because priorities might have changed, but if it's not the center that had the hydrogen abstraction, it's not going to change, okay? So that's an important part. All right, questions on the stereochemistry of radical chemistry. Okay. So RNS, mixture of RNS. Okay, so now let's talk about allylic and benzylic. Remember when we talked about stability of carbocations, we said that tertiary carbocations were the most stable until I told you about the resonance possibility structures in allyl carbocations and benzylic carbocations. It was all about the resonance structure. Well, it turns out the same thing happens with our radical system. We get a single electron that gets to go back and forth, one electron from, come on. Okay, there we go. All right, one electron will come from the double bond and go over to this side and use the radical on this side to create a double bond, creating a radical on this carbon. And since those are equal in resonance energy, they resonate back and forth. And that means that you get half of your radical on one and half of your radical on the other. Of course, this leads to products because in this case, they're equal because they're going to be both on a primary carbon. So you're going to have that last reaction happen on a primary carbon. But when they are like this, you have stability, and that's why they're more stable than the tertiaries. And if we look at the benzylic, we have actually 5 resonance contributors where we can put that radical. Now, the radicals on the chain here can react, but most of the time the radical spins it here. So this is where we typically get our primary product, our major product. We'll get a little bit of halogenic or reaction around the ring, but rarely do we have it. We usually have it contributing to this benzylic radical, and our product ends up on that benzylic site. Okay. Okay, so that means we have to update our stability of radicals. Benzylic and allylic are about the same because of conjugation. Then we have the tertiary, the secondary, the primary, and we can make primaries and vinyls and methyls because the stability difference is not as big as it is in carbocations. Okay. What does more stable mean? More stable means that it forms faster, meaning you have a greater yield. So now we're starting to talk about regioselectivity of where your last thing comes on, usually the halogen, because usually you start with radical abstraction to get that to go on there. And so that's where we get them. And so we have higher rates of formation for benzylic and allylic cations, but what if you have an unsymmetrical molecule? Now you're going to have selectivity. So let's look at these two right here. All right, so if we started with our radical abstraction out here on the secondary carbocation, we're going to have it resonating back and forth, but look at this. This is a tertiary radical. This is a secondary radical, okay? So we're going to get more product on this site, even though this site is much easier to do the abstraction with. It's much easier to abstract the hydrogen on this secondary site because of sterics, but we're going to have more of this tertiary product because of the resonance stability and the fact that it's a tertiary tertiary radical instead of that. So we're going to get more of the tertiary product. Now, if we move where that radical is, we have a choice between having a primary radical or a secondary radical here, which means we're going to get our substitution at the secondary site because the secondary is more stable. It's going to spend more time there. Okay, so we're going to get our major product is going to be with this radical on this side. Our major product is going to be a radical on that side on that. So that can be a little problematic. So you might have to draw both of them and say this is the major product and the less stable radical is the minor product. Okay. So let's talk about this halogenation of benzylic and allylic cations. We actually can do a really cool thing in the fact that we can start with just benzene, do a little bit of heat with a halogen, chlorine or bromine, and it will halogenate right at the benzylic position, the carbon right next to the benzene ring selectively, and generate some acid, okay? So unfortunately, sometimes there's a side product with that. And so we actually have another way to do it where we use a compound called NBS. Now, the reason we have that is that we can have, if you have a benzylic site, but you also have some double bonds somewhere, you could react those as well. And if you want to be very specific about that, you wanted to get the reaction, we want to have not very much bromine around at all. You want to only have just enough to do your hydrogen abstraction and your reaction. And when we do that, we replace the bromine by itself with a thing called NBS, N-bromosuccinimide, okay? So look what we have here, N-bromosuccinimide. It has a nitrogen-bromine bond, okay? Well, it turns out that's a pretty easy bond to break, and so we're going to use that to our advantage. Now look what the substrate we have. We have cyclohexene, okay? So if we had cyclohexene, we don't want to add bromine across that double bond. We want to preserve that double bond and do the allylic substitution. Fortunately, the allylic substitution is faster because it's more stable, but we don't want very much bromine around at all. And so what we do is we change the system. We use light, heat, or peroxides to do this, and we can get selective substitution at the allylic position, not hurting your double bond, okay? So if you have a double bond on something and you have a bromine end up allylic to it, you're gonna use NBS, okay? So how does that work, okay? Well, it turns out it just allows for a very small amount of bromine at any one time, okay? And so the allylic radical forms first, so the bromine is not attacking the double bond. So the allylic radical is actually doing the abstraction from bromine. So let's start with that. We look at our two initiation reactions. We have two here because we have the peroxide, and that just gets us to a radical, but we want to get to a useful radical. So we actually have to do something weird where we use this reaction here, and we break the bromine nitrogen bond into two radicals. Okay. All right. So then that radical can act and abstract a hydrogen from something, or this radical can react and abstract a hydrogen from something, generating our allylic radical. So in this case here, the bromine or the peroxide can do a hydrogen abstraction allylic, giving us our allylic radical, which is more stable, okay? And then it usually produces either HBr or a termination product. Now, some unreacted N-bromosuccinimide can act as a base. And when it acts as a base, it will generate a new hydrogen nitrogen bond and a charge. And then the bromine from HBr or whatever is, if there's any bromine ion around there, acts as a base and goes out and reaches out and grabs that bromine. Okay, so we end up regenerating our succinimide. So this is no longer reactive. And we generated just a little bit of bromine. But while we were generating that little bit of bromine, we also generated another allylic radical. And so the bromine can react with that allylic radical to generate our bromine radical, and that can go back into this step here and keep going and going and going. Okay. Now, there is no termination steps here, but imagine a bromine-bromine radical would be a termination step, but that's reactive, so that's okay. An allylic radical can couple, and that makes a bigger material, not productive. Or we can just go back and start taking hydrogen or whatever. So those would be our termination steps where we're getting rid of those things. Do we see why NBS only generates a little bit of bromine and a whole bunch of allylic radical? So as soon as you form an allylic radical, it's going to do that. And we're going to get that substitution next to a double bond, not reaction of the double bond. Okay, questions on that? Okay, so then that leads us to our regiochemistry, right? We're going to have, if we make unequal allele radical sites, we're going to have regiochemistry issues here, okay? So they often give a mixture of products. And so if we look here, you're going to say, oh, well, you know, if we just added HBr across that, we get bromine on this end here, because it's going to hydrogen abstract there, or, you know, a bromine here for some other reason. Well, when we can form that allylic here, we can actually deprotonate or form our radical here. We can do our hydrogen abstraction to give us our allele radical. The hydrogen abstraction to give us our allele radical is actually faster than our addition across a double bond, or adding to a double bond, because it's more stable. So that means we're always going to get a mixture of products on one side of the allele, and then this is the other side of the allele. Okay, but which one's going to be slightly more favored? The bromine on the one position, or the bromine on the, I guess that's the three position. Three position here and one position here. Oh, yeah. Okay, because this would have been a primary radical, primary allyl radical. This would have been a secondary allyl radical. So a little more stable, so a little more reactive, but we're going to get both products. We will get both products. There's no way around getting both products. And the reason is that we don't have identical allyl structures here. Once we do a hydrogen abstraction, we'll do it here. Because remember, these are less stable. If we did a hydrogen abstraction here, it's less stable. So we're going to do our hydrogen abstraction here, which gives us our resonance structure of going back and forth. So we have it half the time here and half the time here. And while it's here, it goes to the 3-bromo. And while it's on this side, it goes to the 1-bromo. And so we're going to get it. So we get that mixture. Slight favor for the 3, but it is an allylic radical, so they'll get both. All right, questions on that? Okay, so radicals can only do 2 things. Hydrogen abstraction and add to a double bond, generating another radical on the 2nd carbon. Okay, 3 steps in every radical reaction. Allylic and benzylic radicals are more stable than tertiaries, secondaries, primaries, methyls, vinyls, etc. Okay, so what are they good for? If we get mixtures of products, why do we care? Well, remember, we have that addition of HBr with the presence of peroxides gives us the less substituted bromine compound. So that's a really useful reaction. You should remember that. This allylic halogenation, where you can put it allylic to your double bond using NBS, N-bromosuccinimide, that's a very useful reaction. It's very selective right here. This is not as a selective reaction because it can go.
Can you repeat what the 2 things are?
Okay, they can only do 2 things. Hydrogen abstraction to generate a radical, usually on the substrate. sometimes on a bromine if it's HBr, and adding to a double bond, generating another radical. Okay. And then propagation step is you always are generating another radical. Initiation step, you generate your radical using something like a peroxide. And in determination steps, radicals couple to give us neutral, non-radical things. Okay, so what's the most popular way to use this in industry is to make polymers. So there's a whole section here on polymer chemistry, and so I'm going to give you a brief overview from that. So what we want to call, what this is this is just basically very large molecules, okay? That have the same repeating unit over and over. So what we say is a polymer is a high molecular weight material repeating with the same units of smaller molecules, and those smaller molecules are called monomers. So you can think of mono meaning one. If you had two of them hooked together, that'd be a dimer, trimer. But if you get so many you can't count, then it's just poly, which means many. And so we have polymers. And so these are very large molecules, and they're very rigid repeat units. And so most of the we do these polymerizations, when you do a quote, a polymerization, that means you're hooking molecules together to make large molecules, okay? So the great thing about a radical polymerization is once you add to your double bond, it generates another radical, which can then add to a double bond and generate another radical, add to a double bond. And just imagine it's going zzz, up. Every monomer available gets zipped up into a polymer chain. Okay, so we have a wide range of vinyl monomers we can use. We can use anything that has a double bond in it. Z could be a hydrogen, Z could be a chlorine, Z could be a phenyl group, Z could be a hexyl group. It doesn't matter. But we'll see that we get these all react in that same reaction mechanism. Now, Z affects the properties. For example, if Z is hydrogen, we get polyethylene. Think of plastic grocery bags. That's polyethylene. But if we put a chlorine there, we get PVC pipe, or plumbing pipe, really rigid, strong plumbing pipe. So that's just changing one thing, and we're getting that very different. Put a phenyl group there, you get really clear material called polystyrene, or foamy stuff called polystyrene. So that's just changing that one thing. They all use the same mechanism. So we're going to learn the mechanism, which we should already learn the mechanism, but I want to show you the mechanism. And what we see here is in our polymerization, we can take, in this case, just 3 little monomer units, do that addition, create a radical, addition, create a radical, addition, create a radical, and they'll zip up together in an ordered fashion. Notice the groups are all in the same place. Okay? The groups are all in the same place. Those Z groups are all in the same place. Because one of these two sides is going to be the more stable radical. Usually it's where the Z is. So we're going to give more stable radical here. So that's going to attack the front end of the next one, generating a radical here, which is going to attack the front end of the next one. So you're going to see that regular pattern attack from the Z, wherever the Z is attached, to the less substituted side to generate the new radical where the Z is, which keeps going and going and going and going. And we call this head-to-tail polymerization. Okay. So let's look at the mechanism a little bit more in detail here. For more substituted, radical always is, to the less substituted into the monomer. Okay. So just what I said, our head is going to attack the tail. And so in this case, we can just call the Z radical the head, because it's doing the work. It's going to attack the tail, the less substituted side of a monomer. So we're going to start everything like we always start radical reactions with our initiation step. And in this case, we can use peroxides. It takes a peroxide or something like that to generate. The monomers themselves are not reactive enough to form radicals, so we have to use peroxides. And so we get our generation of our first radical on a carbon here. When that peroxide reacts, adds across that double bond, remember, 1 electron moving here, 1 electron moving here, generating a new sigma bond, and then generating the radical on the other side. Now this radical can attack the tail of the unreacted monomer, and it will generate a radical. And it just keeps going and going and going and going. So let's talk about that property a little bit of if we had just hydrogen at this, that's polyethylene, that little grocery bag. Okay, so if you go anywhere below 4 carbons of an alkane, it's a gas. And then 4 to about 12 or so, it's a liquid. And then over 14, it's kind of a wax. And then it gets tougher and tougher and tougher. The properties change until you can make plastic bags out of it. That's a million repeat units. Okay, so going up from just, you know, butane is a gas, hexane is a liquid, dodeca is a wax. 500 of them is a kind of a waxy solid. 1 million of them is a strong plastic bag. Okay, so that's how properties change in our polymer system. Okay, so let's look at a couple different common ones. And in this case, we're looking at the first one is the vinyl chloride. And so polyvinyl chloride is how it's named. So PVC, that's what that stands for. And we again get that same perfect pattern. Our Z right here is going to generate our secondary radical here. It's going to attack the primary side of the other alkene, of the non-reactive alkenes, to generate this perfect pattern where we have. Now, one thing I want to draw attention to is that this bond right here is the bond we just formed. This bond is the bond we just formed. This bond is the bond we just formed when we did that. And each time we generated a radical on this carbon here. So that's where our new sigma bonds are coming from that radical attacking this side, generating our new sigma bond plus our new, one barb, generating our new radical on this side. Okay.
On a 3D spectrum, like what would that look like? You could just go like in the ring, like with the CLs be popping out.
Let's see, they're not technically chiral because if you're going to either side, that can change based on catalyst. Usually they're alternating, but you can do them all on the same side or all on opposite sides with some systems. Not this one, but now things get more complicated when you react it with 2 alkenes. Okay, you think, oh well, you know, it'll just add across this side or add across this side. Well, it turns out when you react isoprene to generate its first radical, so let's say we take this and I'm going to change to red. We're going to come in here with our radical generating our first one barb. Right here, creating our first bond. This electron comes to make our thing. And look, we have our electron come and sit here. It's allylic. So we have an allylic tertiary, and look where it would spend half its time here and half its time here because of the 1 electron over here. And so our double bond can end up here in the middle part of the time with its allylic. Well, it turns out when the radical's up there, it's kind of crowded. It's stable, but it's crowded. And so what happens is this radical then comes and attacks one of the other ones. And so what we end up with is our new sigma bonds, which I'll do here, are in between these, but we still have a double bond. We have a very stable, highly substituted double bond, but we end up doing that. So this is basically synthetic rubber. Synthetic rubber is isoprene, which is where we take that and we do our addition to generate our radical here, but then we have it out an allyl radical, which means this side is less sterically hindered, attacks the next one, creating a sigma bond, which attacks the next one, creating a sigma bond, which attacks the next one, creating a sigma bond. Okay. So, oh, this is natural rubber, sorry. Isobutylene is the one that creates synthetic rubber. It's not very good. Okay. So, styrene. Okay. Now we know that benzylic radicals are very stable. So that means when we get our first addition of an electron here, our electron coming out here to generate that and getting here. Now we have single barb, our nice stable radical. And again, it's going to attack the head here. And so our repeat unit is going to look like this. Right here. And so when we have a repeating unit, we can put a little bracket around the one that repeats and just add an n there. The n means some number. We don't know what the exact number is. We just know it's poly, more than a few. And so we can do that. All right, questions on that? Okay, so now in the book, they actually cover something in the radical chapter that's a little different. We can actually polymerize the same vinyl monomers using a different mechanism that does not involve radicals.
So just to, are you saying that like these C5 rubber are organic compounds?
They are, yes, they are organic compounds. They contain carbon and hydrogen.
That's crazy.
Well, I mean, the polyester there is a polymer, and this is a melamine, which is a polymer. Trees technically are polymers. Cellulose is a polymer of sugars. Proteins are polymers of amino acids. Fats are polymers of fatty, well, not technically polymers. They are triglycerides. They are triesters of fatty acids and glycerol, which is 1,2,3-triol. Propane triol. So really, most things around you are. Concrete's not. It has some carbon in it, but it's not an organic compound. Most rocks aren't, but a lot of the stuff is. Paint's organic compound with a lot of solids put in it. Okay, so let's look at this other weird mechanism here. Okay, so this other weird mechanism is we can actually do this by generating an allele, or we can do it with a cation or an anion. Okay, so we can do it by two different mechanisms. And we know that our more substituted compounds make more stable cations. Okay, so in the case of a cationic polymerization, we are going to have something like a Lewis acid, and it's going to generate our first bond here, generating a cation here, which then this is our nucleophile. I'm sorry, this is our electrophile, and our double bond on the next thing is our nucleophile. So it's going to attack there, generating a cation, because both electrons are coming out to make this sigma bond. See how that mechanism is different? We had that pi bond, and when we used a radical, only one of its electrons came out and gave us a sigma bond. In this cationic one, both electrons come out, giving us our sigma bond and generating the cation here, which then reacts with the next one, and reacts with the next one, and reacts with the next one. Okay, so this works best if there's an electron withdrawing group on there. I'm sorry, an electron donating group on there. Why? So if we make a cation right here, we saw that if we had carbons, that would have been a horrible recording. Okay. So when we looked at carbocations, we wanted 3 other carbons around it to help donate electron density to stabilize that cation, right? So in this case here, when we generate the cation here, to make it more stable, because it's only a secondary cation, what if you had an oxygen that could donate electron density to it to stabilize? So if we have a carbon or an oxygen there, it actually can make that carbocation more stable as a tertiary, and then it can react selectively because it's more stable. Okay. If you have electron withdrawing groups, though, we can do it backwards. We can do what's called an anionic polymerization. And in that case here, what we have is our electrons are going to be coming from whatever starting it. Let's say we're going to start it with ammonia here. These electrons are going to come in here, both electrons. Then both of these electrons are going to come out, giving us an anion. Then this is our new anion. And then we can have another one over here. And these can go both electrons here, both electrons forming another anion here. So because of that, we want electron withdrawing groups there to stabilize that charge. We have an anion, but it's going to be more stable if we can dump some of that on a neighboring atom. Okay, so these are similar mechanisms to our radical, right? We start with a cation, we keep generating cations until we run out of material. We start with an anion, we keep generating anions until we run out of material. We start with a radical, we keep adding and getting radicals until we run out of material. All right, questions on that? So that's everything you need to know about polymer chemistry this semester. All right, so that's the end of chapter 10. Okay, so let's move on to chapter 11. Chapter 11 is a long one. We've got a lot of new reactions here. 11. And we'll start with taking roll. Creeping up a little bit, just over 5, first time in 3 weeks. So anyway, keep it safe out there. All right, let's go back to, okay, so this chapter is our last chapter. We have to come back to nomenclature because we haven't done a lot of nomenclature up to now, so we're going to come back to nomenclature. We're going to do our alcohols. We're going to do a nomenclature review before the final and before the exam, so I'll make sure that we have that. So we're going to look at alcohols and ethers, and they have slightly different reactivities, which is why we're going to talk about them slightly separately. Okay, we have different classes, subclasses of these alcohols. And so if it's just an alcohol with no double bonds nearby, no phenyl rings nearby, and stuff like that, then we call them just alcohols, okay? If you have an alcohol that is next to a double bond, we call those enols. Enols. So it's an alcohol, but it's an alkene. Remember we did, when we had an alcohol and an alkene, we called them an enol, but when we just as a general class, we call them an enol. Okay. And when we go in the next chapter is carbonyl compounds. So 12, you're going to start with carbonyl compounds. You're going to learn something about enols and carbonyl compounds. The other thing we have is if that OH is bonded directly to a benzene ring, they're called phenols. Okay. And what we found is that when we looked at acidity, phenols had a pK of 10, alcohols had a pK of 15. Phenols were more acidic because of the resonance structure, and so it has different reactivity and a higher acidity. Okay, so in the case of that, we also have a bunch of other ways to look at these. We have a couple things that are common names. So in the case of this is not an enol. Okay, why? Okay, both of these cases, these are sp2 hybridized carbons. sp2 hybridized carbons. This is an sp3 hybridized carbon, so it is not an enol, it's just an alcohol. Okay, and we have 1, 2, 3 carbons, and we have the alcohol on the 1 carbon, and the double bond starts on the 2 carbon. So it's propene 1-ol. or 2-propanol, propanol. Okay, but it's more commonly known as allylic alcohol. See how that allylic group, that common name for that allylic group we had for the radical and the cations and everything like that, it's used there. When we use our common names, it's going to give us the common fragment plus alcohol. So in this case here, this is a propyne with a carbon here. We call this propargyl alcohol, or prop-2-ine-1-ol. Okay, and if we have it in a benzylic position, remember here, this is the allylic position. It was allylic alcohol. If it's in the benzylic position, we call that benzylic alcohol or benzyl alcohol. All right, questions on that? I'm not going to go over the full nomenclature, but I'm going to go over full nomenclature on the review. Okay, so now when we have ethers, that's a different structure. We lose that hydrogen bonding hydrogen, and we now have carbon, oxygen, carbon bond. Okay, so we lose hydrogen bonding, and when we do that, we just name ethers of the 2 alkyl groups bonded to the oxygen and add the word ether. So if it's symmetrical, you can just call it diethyl ether, because there's 2 ethyl groups and it's an ether. If it's unsymmetrical, you can call it ethyl methyl ether, because it's alphabetized. Okay. Okay. We talked about alcohol naming, but we haven't really talked all about the ether naming, so I'm going to go into that a little more complexity. Ethers do not change the parent name. They are only ever a substituent. Okay, so if you have anything that has the number of carbons plus oxy in it, that's a substituent. That's an ether substituent. Okay, so we're going to look at the number of carbons it has and then put the oxygen on it and know it's always going to be a substituent. So when we have 1 carbon, that's meth. Oxygen is oxygen. So 1 carbon plus an oxygen is the methoxy pendant group. Okay, 2 carbons, ethoxy. If you had an isopropyl group, there would be isopropyl oxy. In the case of this T-butyl group, T-butyl plus oxy, T-butoxy or tert-butoxy as the functional group. Notice it's butoxy. It's not what we had when we made the salt out of T-butyl alcohol, which was the T-butyl alcohol salt thing. Anybody? Bueller? Okay. No, okay. Anyway, so what we do is we take the parent, we find the parent, and whatever the parent is, and then we have to locate our substituent. So in this case here, we have 1, 2, 3, 4, 5. So we have pentane, no other functional groups. So it's an ANE at the end, no double bonds, no triple bonds, nothing else. Okay, but we have to locate our thing here. So numbering from this side is lowest. So we have 3 methoxypentane. Notice it runs all the way together and you don't have to capitalize it. What?
So 3 is it 2?
I said 3. 1, 2. Oh, it's 2. 2 methoxy. Sorry. Now, what if you have 2 ethers there? You have to find the parent. Well, this is an ether here, and this is an ether here, which means this is their parent. So it's ethane. Ethane is our parent. And so we have 2 ether groups. One's going to be on the 1 carbon, one's going to be on the 2 carbon. 1, 2 dimethoxy ether. So all the other rules apply. It's always a substituent, like a chlorine or a nitro group. They're always a substituent.
How can you know to say like oxy on a test? Like, how could you really tell? Like, just because it's bonded to the O?
If it's got a carbon, oxygen, carbon bond in it, you have one of those 2 sides is going to be shorter. And whichever side is shorter is the pendant group. So let's look at how we would IUPAC name this one up here. Okay, so this would be, well, let's see, we have ethyl and we have an ethoxy. So this would be 1 ethoxy ethane, or the common name diethyl ether, which is why people use it. Or in this one right here, this side is smaller than this side. So that means our substituent is there. So this is going to be our methoxy side of it, and this is going to be our ethyl, ethane. So it's going to be 1-methoxyethane. Okay, so what I do is I actually literally draw a line where that oxygen is and note it. This side is going to be the something oxy, and this side is going to be the parent chain. Whichever side's longer, if you have a difference. Okay. Okay. So ethers are pretty easy to remember, but there are some common names that we need to worry about. They are so ubiquitous in industry and stuff that people have to look at it. So when they're both the same and they're bonded to the oxygen, you can just say di something ether. Okay. If they're not, you list them alphabetically and add the word ether. But notice when we use common names, it's just the alkyl group. The word ether takes place of that oxy. So we're going to say on this one, we have a methyl group, we have a sec-butyl group. So that's going to be, remember, sec doesn't count for alphabetization. So we have sec-butyl space, methyl space, ether. So it's really easy to see if you have an IUPAC name because there's no spaces. You have dashes, numbers, brackets, commas, ends, but never do you have a space. Common names have spaces. So in here we have our diethyl ether to the symmetric. Now, we also have some cyclic ones, okay? The first one here is, the proper name is oxycyclopropane, saying you have substituted 1 oxygen for 1 carbon in cyclopropane. So oxycyclopropane. But the most commonly known as ethylene oxide, or by another name we're going to use, epoxy. It's an epoxy group. Okay. There's usually something else attached to it here to make it an epoxy group, but we're going to have a whole section on epoxies.
Is it like the floor?
Epoxy, well, yeah, this is the functional group that is in that material that makes the polymer. Okay. So if you just substitute 1 oxygen in cyclobutane, it's oxycyclobutane or oxetane right here. This one's kind of important because we've seen this one before. This is one of our polar aprotic solvents. Okay, it's technically oxycyclopentane, or we call it tetrahydrofuran. And that's because it's made from this heterocyclic compound called furan. And what we're doing is we're adding 4 hydrogens to it, which gets rid of the double bond and makes it tetrahydrofuran, or hydrogen furan. Okay, so, or THF. This is an important one to remember because this is one of our solvents. Okay, and when you have 2 of them here, this would be, let's see, dioxycyclohexane, or this is dioxane. Okay, you may have heard of dioxanes building up in the water and stuff like that. Turns out those are benzodioxanes. And those look like this. And most of them have bromines and stuff on them. That's the stuff that builds up in the environment. This is a pretty decent solvent. And it can also be used as a polar aprotic solvent. Okay, questions on those? I would remember all of those cyclo names, because those are not like the systematic names that we have. So, okay. So let's talk about epoxies. Okay, it's our first ether. It's really weird. If you think about an ether, they're actually very chemically stable. It's hard to attack them with acids or bases because you're going to have a leading group being a carbon anion or a carbon cation or an oxygen anion or an oxygen cation. So those are very bad leading groups. So they're very unreactive, except for this one. Why? Ring strain. Yeah, it's on down the page. If you read fast, you'll see it. Ring strain. So, well, it doesn't want to react because it likes having those nice stable bonds. The fact that is it can spring open and generate an anion on the oxygen when it springs open. And that's a stable leaving group when you do it. So what we're going to see is we're going to see substitution reactions, SN2 reactions on these rings. Okay. Now it has everything to do with the fact that we are straining these bonds. They're practically bent. They're not bent, they're just practically bent. and it just wants to spring open as fast as it can. And so they're very reactive species. And so most nucleophiles will react with these at room temperature. Hence, you have two-part epoxy, okay? In two-part epoxy, one of them is something with 2 or 3 different epoxies on it, and it's this non-stinky side. And then the other side is has a nitrogen containing compound that acts as a nucleophile. Okay, that's the stinky side. And so when you mix them together, the nucleophile starts reacting with the peroxide ring and opens it up to give you an alcohol and a new carbon-nitrogen bond. And that's how you have epoxies. And usually a multifunctionality, so it's all, there's no way to dissolve it, and it won't crack, and it's really tough. Okay, so let's talk about epoxide nomenclature. Okay, so the reason we have so many names for these, and we call it the epoxy or whatever, is because they were used in industry, and so they have kind of an engineering style name to them. So we kind of need to pay attention to that. So one of the things that we see here is that I called it on the first slide ethylene oxide. Okay, and that's because it started from ethylene, and then they made it to ethylene oxide. So that's why it's called that. Okay, and the true name is oxirane right here, or oxypropane, oxycyclopropane, etc. Now, the common name is, okay, so if we had this double bond and we put an oxygen across it here, we would have propylene oxide. So the common names are based on the alkene you would have started with to put the oxygen into that ring. Okay, but in systematic names, we want to talk to where our location would be. And our location that we're going to do is, like an alkene, we want to have the lowest numbers possible for our oxirane. Okay, and so that means the first carbon that our oxirane starts on is the one that locates it, and then the one that follows it is where the other bond to oxygen is. So in this point right here, that makes the oxirane change the name of the compound. The oxirane is a cyclic compound. Remember, when we have a cyclic compound, if it's bigger than the main chain, you name it for that. So we're naming it for the cyclic compound, the oxirane here. And so this is going to be the 1, this is going to be the 2. And so that makes this 2-ethyl oxirane. Or if we were going to use a common name, we would call it epoxy, 1,2-epoxy butane, because there's a total of 4 carbons. But we're naming it for the ring in systematic method. Okay, so in this case here, our oxirane is here. So that means we have a methyl group on one side of the oxirane, a methyl group on the other side of the oxirane. So we have, it should be 1,2-dimethyloxirane. That's wrong. 1,2-dimethyloxirane. Okay, because this is the 1 carbon and this is the 2 carbon. Because we're naming the oxirane. Oh, actually, that's not true. Aha. Where do we start numbering in a ring? The thing that's different. 1, 2, 3. 1, 2, 3. Okay. The oxirane takes the oxygen takes the 1 position. The first substituent takes the 2 position. The second substituent takes the 3 position. So we have 1, 2, 3. So it is 2,3-dimethyl oxirane. Okay. So this one makes it a little bit more easier to see. We're going to see our 1, 2, 3. So this is going to be 2,2-dimethyl oxirane, or methyl propyl epoxy. Okay, so in that case, when you do it systematically, name 2, the second one here, you're going to find the longest parent chain, including both carbons of the epoxy. And you're going to call it, the epoxy is trying to be on the lowest number, 1, 2. And then whatever substituent you have that isn't on that main chain. So here, we actually have the butyl, because we have the epoxy butane, because it's 4 chains, and it includes both of the carbons of the oxirane. Here, this has to include both carbons of the oxirane, giving us our longest chain is only propyl, making this methyl group a substituent. Okay.
Just wondering about that.
And so in that one, this one's butyl, but it's 1, 2 epoxy butane, 1, 2, 3, 4 for butane, 1, 2, 3, 4 for butane, 2, 3 epoxy butane.
So that's accurate. When did it happen? 2, 3 on the second one?
Uh,
No, third one, sorry. Third.
On the third one, no, because we start number from here, 1, 2, and then 3.
But on the longest chain, the substituent is
Oh.
number 2.
Okay, so this is numbering system for that one. The numbering system for the green one is 1, 2, 3.
Oh,
Because we're calling the epoxy a group, an attached group. So see, it's up here, it's the constituent, meaning their alkane is the parent. So is that the, we get the numbering system? When you say oxirane, oxygen is always number 1. Okay, where are we? Oh. No, I got 5 minutes. All right. All right. So let's review how to make some alcohols. We've learned how to make alcohols before, and we're going to use some of these in this chapter and add some new ones. Okay, so we can do the sulfuric acid and water, or dilute sulfuric acid with water, or sulfuric acid catalyst with water. And we always get the more substituted because it goes to that carbocation intermediate. We can do the same thing with alcohols to make ethers. Same mechanism, except we don't have that water in there. We do the reaction in methanol or ethanol, and then we can get an ether on there. And again, we have a carbocation rearrangement, and we get the more substituted ether on this case. Then we had our mercurization, demercurization, where our mercury adds to our less substituted side. We get our alcohol on our secondary site, or the more substituted side, and it does not rearrange. It does not rearrange. There is no carbocation. So that's how you can get your secondary. We can get our ether by using an alcohol instead of water. And again, it does not rearrange. The alcohol is going to attack on the other carbon. The mercury was closer to this side over here, and we get reduced off at the end. And then, of course, our hydroboration is the only way to get to our primary very easily. So our primary, our secondaries, and our tertiaries all go through different mechanisms to give us our different alcohols. Okay. So now we're going to do some other reactions, what we've seen before. We saw these in number 6, chapter 6, SN2. If you have a good nucleophile and an unhindered alkyl halide, you can make a substitution product. So look at this, is very good for unhindered primaries. Occasionally you can get it to work in a secondary, but by the time you get to a secondary, it wants to do E2. So here we're going to do SN1, SN2 with these 3 nucleophiles to generate an alcohol if we use hydroxide, an ether, and this one's an unsymmetrical ether because we're using a propyl group on one side and a methoxide as our attacking ion. And on this side, we can make symmetrical ethers. See, we have a ethyl group on the bromide side, an ethyl group on the alkoxide side, giving us symmetrical ethers. Okay. So if we're getting these ether reactions through a nucleophilic substitution attack, specifically SN2, that actually has a name. It's called the Williamson ether synthesis. Okay. And it's used specifically for making ethers in high yields. Okay. But we need to make sure we prepare our alkoxide correctly. Okay. Because we want to make sure that that is our only nucleophile. Okay. And the best way to prepare that is to actually react it with something like sodium or potassium metal. What's going to happen is it'll do a single electron transfer and end up evolving hydrogen gas, and you'll have pure sodium or potassium epoxide right there. Now, you can do this deprotonation with any base stronger than your alcohol, which means you can kind of do it. You can't do it with hydroxide Hydroxide was, if it look at its conjugate acid, it's pK of 15. The alcohols are pKa's of 16 to 18. So they are more basic. You cannot make it with the alkoxide, but you can make it with anything higher, like the acetylide ion, the amide, or the alkyl or vinyl halide, or I mean vinyl bases or anything. So a good way to do that is to take your material, add sodium amide to it. It's just going to create that, but you have to make sure you add the amide first and let it completely finish reacting. And then you add your alkyl halide and generate your ether. All right, people are putting stuff away, so I guess we'll save the rest for Monday. Have a safe weekend.